Okay. So last time we saw BFS and some applications for finding shortest paths in unweighted graphs and checking whether a graph is bipartite. And towards the end, we discussed DFS, and I was leading towards an application for DFS to find cut vertices in a graph. Right? So let's recall how DFS works. Let me write the code for DFS, and then we will add more things. We first color them white, and we also initialize. This is the parent pointer. First we color them white, and then I'm going to start exploring from white vertices. This is exactly the way we did it for BFS as well. Right? So for V in V, if color of V is white, then I'm going to say DFS V. Okay. Yeah, so let's, since I've already used DFS of G, I'm going to say DFS visit V. Okay, and DFS visit V, like we did in BFS, so it's going to start exploring from V. So I'm going to first color the vertex gray. Then I look at neighbors of V. If color of U is white, then make its parent okay. And after doing all this, I'm going to say color of U is black. Okay, so it's exploring in a depth first manner. So I start by, so moment I'm going to start exploring a vertex, I color it gray. Look at all adjacent white adjacent neighbors. Make their parent to be this vertex who caused it to going to be gray, and explore from there. Okay, it's a recursive algorithm, so I'll call from there. And after I'm done with all adjacent neighbors of V, I'm going to color V black because V has been done, explored with, all the neighbors are done with. Okay, so this is the DFS algorithm, and how much time does it take, first of all? Okay, it's a recursive algorithm. But as I said, you can implement it using stack and then makes the analysis simpler. But another way to think about it is how many times this DFS visit at any vertex is called. Let's look at this statement. In this, let's look at this statement, how many times it's called. It can be called. At most? No, overall, not in one instance of the for loop. I'm talking about, I'm trying to do an aggregate way of analyzing it. So overall, how many times this statement would be executed? Okay, why?
Every time it's going to our if it's white.
Yeah, so it's one at most once per vertex, because the moment you are exploring, the color becomes gray, and then you will never come and explore because you are exploring only white vertices. So this is called at most n times. Okay. So if I remove this out, then it looks very similar to the BFS thing, that for every time I'm calling this, it's sum of the degrees. So it's order m, and then everything else would contribute order n. So it's order m plus n. It requires, because it's recursive, you need to analyze this carefully, but the idea is more or less same. You can view in terms of implementing by a stack instead of a queue as we did for BFS, or just say, okay, I'm going to count this separately out, and then the rest is sum of the degrees. Okay, so this is order m plus n time. And we looked at how the edges of DFS are, right? Non-tree edges of DFS. In undirected graph, these are like back edges, right? From a descendant or between an ancestor to a descendant. That's how it will be. We'll do an example because I want to add more things here, and then we'll do a comprehensive example. So all I'm saying is that if you look at your, non-tree edges, you can have an edge from this vertex to somebody like this, an ancestor, right? Because I didn't explore this because it was already black, and I didn't explore when I was here because this guy got explored all the way and came here. But you cannot have cross edges, and you cannot have an edge like this because that edge means that that vertex would have been explored when I was trying here, and okay, and yeah, and the way to think about DFS tree is you start from a vertex, go deeper, as until no longer possible, then go backtrack, and go from here. That's exactly what will happen here, because you will take a vertex, go to its neighbor, and then visit, finish, and then the control will come back to the latest for loop you had, and it will go to the next adjacent vertex and see if it's white, and you can explore, finish all that. Then that's how we use a stack, right? So once you finish, no more adjacent vertices, you come back, then this was an adjacent to this, then it will go and explore the next adjacent vertices from here and finish off, and then you go to the next adjacent vertices and so on. Okay, so okay, in a directed graph, so you can have back edges like this. So maybe instead of saying between, I would say from to, because it's a directed graph, from an ancestor or from a descendant to an ancestor. That's why it's back edge, or even forward edges. Forward edges are of two types actually. It could be like this, from an ancestor to a descendant, or it could also come from some other vertex, right? I mean, you grew DFS, and then maybe it's coming from some other DFS tree, and it has an edge to this. Okay, this also is like a forward edge. Okay, it's coming from yeah. So when you are exploring this is already black. Yeah, so an edge UV where V was black when U was explored. So there are two types of this kind. Okay, so now let's look at some applications. Also, it's useful to compute a couple of more quantities in DFS. The first time a vertex, so I want to have some timestamp on the vertices. The first time I find a vertex, I'm going to give a discover time, and once I finish with that vertex, I'm going to call it a finish time. Okay, so it will be time, I'm going to time plus 1, and discover time. So V has been discovered at this time. And once I finished with this, time is time plus 1, and V is finished at this point. Yeah, and here you initialize time to 0. And this, these two quantities, the parent pointer, the discovered time, finish time, are all useful. Let's understand some properties with the discover time, finish time. Okay, so let's do an example. And then we'll get to computing cut vertices, right? Okay, so let's just pick some. So let's say A, B. It's directed graph. So let's start my DFS at A. So then A is discovered at timestamp 1, because this guy would call here, and this would make time to be 1, and discovered time, the V is A. Okay. Then A goes to D, and D is discovered at time 2, and D has no more neighbors because it's forward neighbors. So D is finished now at this point at time 3. Then we backtrack, and then we look at C at timestamp 4. C can go to E at timestamp 5. E has no more, so I will finish E at 6. And C has another edge F at timestamp 7 and finish that at 8. C has no more, so I'll finish at timestamp 9. Come back to A. A can go to B at timestamp 10. And I got them all. Right? So finish B at 11 and finish A at 12. Okay, so I have, this is the discover time, this is the finish time. I mean, if some vertex is not reachable from A at all, I have some, I'll follow this, grow my DFS at somewhere else, start at that time, finish, and so on and so forth. So it'll be like this. Okay. So what are some properties? D of V is strictly less than F of V. And here is an interesting property. So if V is a descendant of U, so V is a descendant of U in the DFS tree, then what can you say about this is V? What can you say about their DF values? What I want to claim is DF U. You discover U first, and then you discover V, and then you finish V, and then you finish. Okay, so this DF value is sitting entirely inside the DF interval of U. All this can be formally proved by following through the DFS algorithm, okay, because that's the one it assigns D and F values. And if this is not the case, or equivalently, if the two intervals don't overlap, that means that this is not a descendant of this, that's not a descendant of this, and you cannot have somewhere in between. So these intervals are, one is entirely contained in the other, or they are completely disjoint. Okay, again you can prove all this. So this is a useful thing. So 4, 9 is sitting entirely inside 112, and 2, 3 is sitting inside 112, but 2, 3 and 4, 9 are completely disjoint. Okay, so it's not possible that you will have 2, 4 for somebody and 3, 9 for somebody. Right? This is not possible, because then it's like, yeah. So 5, 6 is entirely sitting here, 7, 8 is entirely sitting inside, 10, 11 is sitting inside this, and so on. And these guys are completely disjoint. Okay, good. So now let's get on to, so this is all works for directed graphs and undirected graphs as well. Let's get on to some applications of DFS. And the first one we were discussing towards the end of the last lecture was on finding cut vertices in a graph. Okay, this is also called sometimes articulation points. Okay, it's the same. It's an undirected graph. So X is a cut vertex G if G minus X is connected. So I want to know whether there is an articulation point in the graph, or find all articulation points. Okay, a brute force would be delete each vertex and check for connectivity. So that's like order n into m plus n. And we want to see, can we say something using DFS? And so what did we conclude last time? In a DFS tree, root is a cut vertex if and only if it has more than one child. Yeah, if it has one child, then it's not a cut vertex. Yeah, it has more than one child. Why? Because of the way the non-tree edges are structured in an undirected graph. They cannot be cross edges. They can only go from descendant to an ancestor. So if a DFS tree has more than one child, then this subgraph and this subgraph are become two discrete components if you delete this vertex, because there is no way you can go from here to here. Because any non-tree edges are like this. They can go like this. Okay, what about for other vertices, right? By same kind of a reason. A non-rooted vertex X is a cut vertex if there exists a child of X, child Y of X in the DFS tree. We're talking about in the DFS tree. We don't need this example. So here is your DFS tree. So I claim that this X is a cut vertex means that, let's apply the same logic as we did for root, right? Basically this component and whatever this component, there are no edges between them here, just as we argued. But they could still be connected even if you delete X, if there is some edge going like this. Right? So X is a cut vertex if there exists a Y that has the following property. There is a child Y of X that cannot or has no path to a vertex above X through its descendants. And a back edge. So in other words, X is a cut vertex. If I look at all vertices reachable from Y in the following way, you're allowed to go as, use the tree edges, and then you can use a back edge. Okay, so I'll use some tree edges and then I'll use a back edge, and if all of them just get stuck here itself, nobody, there is no path from Y to somebody above X. Okay, I have to say all this more precisely, and that's where the D and the F values, D values will come into play in particular. That I cannot reach from Y to somebody above X. What do you mean by somebody above X? Their discover value is less than the discover value of X. The D of that. So if you can, so look at the lowest D value you can reach from Y through the following kind of paths. You are allowed to use some tree edges and then use a back edge. Okay. And see how far you can go. If you cannot go above X at all, that all your paths end up leaving, somewhere here, then when I delete X, this guy becomes a separate component. You cannot connect to somebody else, so this becomes a cut vertex. Okay, so let me say that more precisely, then we'll see how to compute that thing, right? So So let's define low of a V, a vertex V is equal to min of D of W where V to W is a path using tree edges and a back edge. Right. So for any vertex V, I look at, I'm going to use the tree edges and then I use a back edge. And I might use some tree edges and use a back edge. I may go here. So what is the lowest minimum D value I can reach through such a path from V? That is going to be called low of V. Okay. Then, so this is the picture, right? So from V, I'm allowed to use some tree edges and then I'll take one back edge. Then U is a cut vertex if and only if there exists a child V of U such that low of V is greater than or equal to, what should I write? So U is a cut vertex if there is a V whose low value greater than or equal to D of U. That means that through this path, the maximum I can reach is U. So when I delete U, this becomes a component by itself, disconnected from the rest of the graph. Okay, so this is a non-root U. I mean, child when I say in DFS. So one direction is clear that if low of V is above, then U is a cut vertex because this becomes an isolated thing. And conversely, if U is a cut vertex, if you delete U, there is some component which is, it breaks into multiple components, and you look at, since G is a connected graph, you look at a vertex reachable from U in one of the components, and you can argue that it will be looking like this. Okay, so now our algorithm is about finding such vertices. So in particular, I want to compute low values, and what we will see very easily with small modifications that this low value can be computed on the fly as I compute DFS. There's no problem. Once I compute low value, then this is a simple check. For every vertex, I know the D value and the low value. Then I need to run through my DFS, see for any vertex, do I have a child whose low value is greater than or equal to my D value, and then I know I'm a cut vertex. Okay, let's go back to the DFS routine and see how I can compute the low values. Okay, so to keep this definition in mind, so first time I am visiting a vertex, I am just exploring, right? In my DFS, I am growing. So I got the V was discovered. I want to initialize its low value to something. What is the smallest d value it can reach by using tree edges and one back edges? Right now I have no tree edge, no back edge, nothing. So what can I reach? I can reach myself. Right? So low value is equal to d of v. Okay, so that's sort of the, because that is always true. I mean, this is non-empty because I can reach from V to V without anything. So we will update this anyway. Okay. So now I come here, I find an adjacent vertex and I color this, and I've finished. So I'm going to explore U. So let's say I finished with U. Okay. So let's draw. Now what should I do? Wait. So I have V. I picked one neighbor U, and the DFS visit U will call it and finish it, right, recursively. So this is done. And at the end of it, I have a low value for this vertex computed, okay, because DFS visit will have a low value for every vertex anyway at the end of it. So this low value is computed. Now can I use it to update low of V? Exactly. So because at this point I have a low value stored, which tells me from whatever I have explored, what is the highest vertex I can reach, right? Now you finished with U, and from U I know through tree edges what is the maximum I can go. So if this guy can jump above this, then I will update this to this value. Otherwise keep it, right? So here I will say low of V is minimum of low of U comma low of V. That's it, really. There's nothing much going on, because so after I finish this, DFS will call this guy. I will compute some low value, and this guy gets, basically it is updating the minimum. Another way to write this is low value is minimum of the low values of its children. Right? That's what it is. Because anyway, I'm going to use the tree edge, and then whatever maximum I can go through this. And one more thing. Not just that. It's not just the minimum of low values of my children. Through a back edge, I may reach myself without even relying on my children. I can go up, right? So where would that come? Where? No, where are back edges handled here? Gray vertices, they are the back edges, right? If color is white, that's a new vertex. I'll explore, update my color value. The other possibility is that I get a gray vertex, that's a back edge. And then, so I update it with the D value of that vertex. So I come here. So if color is white, I do this. Else, so this else is for this F, which means color is not white. Color cannot be black because I am gray, I'm exploring, so it can't be black. So it has to be gray. If it's gray means that this is a back edge. So I will update low of V to minimum of low of V, comma, not low of U. Okay, I should a back edge. I'm allowed to use only one back edge. Okay. So DF, yeah, right. So if encounter a back edge. How do I know that? Because U is gray. Then my low value updated to, if this guy, the D value of this is smaller, change it. So minimum of low of with my current low to D value. That's it. So it computes this. So using, to be more precise here, 0 or more tree edges, and a back edge, right? So at least one tree edge is where this is happening, that I look at my children and update it, and 0 tree edge is my back edge, right? Direct back edges. Whenever I encounter a back edge, I check the D value and update it. So I compute low value on the fly, really no extra time. It's order m plus n because it's just in the DFS computation you are updating this. And after you've done this, you just check for this condition for every, look for a root node. If it has more than one child, it's a cut vertex. For other vertices, just check this. So you can do a scan starting from the root, looking for these things for its children. So in another order m plus n time after computing low and D. In fact, even this check can be done as soon as you finish. The moment you explode, you just go and say, okay, do I have a child whose low value is more, stays with me? Then I know at that time itself I can do a cut vertex, or I finish this and then do this check. Yeah. Yes. I mean, you are running through every adjacent vertex anyway, and that in that time you are doing this. So it's really, some of the degrees, no extra work, exactly, whatever the DFS time is. Question.
Suppose that B has a backend,
Mm-hmm.
and somebody from its descendants has a backend above B.
So let's actually run it an example also to just see. Yes, but what is it? So you're what?
So B has a backend.
V has a back edge, okay.
And somebody from B's descendant also
Yeah.
has a backend.
Yes, to where? Above this or below?
Above B.
Okay. Above V or above this?
Just above B.
Okay.
Above.
Okay.
Right. So
I mean, this is the definition of low value. It is using 0 or more tree edges and one back edge, how far we go. That's all it is, and that is being computed here. Now you can question this statement. Given that definition of low, let's check whether this is true, if that's what you're trying to do. Okay. So yeah, and it's not saying that low value should be at least D of that vertex. No, I should have a child whose low value does not go beyond me. Beyond me, right? U is a cut vertex. If U has a child V whose low value does not go about. Okay, so let's run an example. Just is this visible? maybe I don't even. Okay, so let's say yeah, so let's say I pick from somewhere, some vertex D, let's say. So it's discovered at time 1, then I visit B at time 2, then A at time 3, C and H. Yeah, by the way, leaves are not cut vertices because if you delete it, there's still, you're not breaking into components anyway. So H is 5 and you finish 6. C has A, D and H. So it can go to D times 7. Oh, D is already visited. So C is done, right? Then come to A. A has B, C done, so that's 8. B is done, A and D, so it's 9. And D grows into E at timestamp 10. Then goes to F, 11, G, 12. G is done, 13, 14, 15, and 16. You agree this is a DFS tree? Okay, so D is a cut vertex because it has 2 children, it's a root. And clearly when I delete D, you have breaks into 2 pieces. Okay, now let's look at the low values. So what are the non-tree edges? Let's write. C to D is a non-tree edge. So C low value is 1 because C can go as far as this. And A has no back edge, but through C it can go, so it has a low value of 1. B has again A and D, and it has, so through A it can go to low value of 1. So H has a low value of 5, right? Because it can reach only itself. There is no back edge, no tree edge. H has a low value of 5. And E, or let's see, start from G. G has a low value. What are the GD is an edge, so it can go to 1. F has no back edge, but through, so it can go to 1. And E again has no back edge, but through these guys can reach 1. So now we will see, is there a vertex whose child cannot reach above? Right. If you look at C, its child H, it has a child H whose low value is greater than, strictly greater than 4. So C is a cut vertex because low of C or low of H is greater than D of C. So H is a child of C whose low value is greater than this. So C is a cut vertex. And is that the only thing? That's all, right? So you have C is a cut vertex. Clearly when you delete it, it breaks it into 2 pieces. D is a cut vertex and there is no other cut vertex. Okay, so this is one interesting non-trivial application of DFS. I mean, you can use DFS also to check whether a graph is connected. You can find a cycle in a graph, find a collection of a spanning forest, all kinds of things. But this is a non-trivial application which you can find all cut vertices in order m plus n pi. Okay, so this is an useful property we'll keep. So let's look at another popular application of DFS is to do what is called a topological sort in a directed acyclic graph. Right? So if you have a directed acyclic graph, and if you do a DFS starting at a vertex, how will the edges be? So I have a directed acyclic graph, so there is no directed cycle. Okay, and I start at a vertex and grow a DFS. Right, so I may not be able to visit all vertices. Then I go to next vertex, grow a DFS kind of thing. So I have this whole DFS. How are the edges of the graph? We know that in a directed graph, the edges are tree edge, forward edge, or backward edges. But in a directed acyclic graph, you cannot have a back edge. You cannot have an edge from a descendant to a forward and an ancestor, because from the starting point you can reach a descendant through a path, through tree path, then use a back edge and you get a directed cycle. Okay, so non-tree DFS edges or forward edges. That means they are, you can have an edge like this. You can have an edge like this, or maybe it's like this. Okay, so you explored this, but this guy was already black, and you have an edge like this, but you cannot have an edge like this. Okay, so this is going to be useful. So now what can you do in a directed acyclic graph? You can do what is called a topological sort. This is again a very useful subroutine. That okay, so it's directed, no directed cycles. Then what is this? This is an ordering pi of the vertices such that whenever there is an edge, the edges are going forward. And you can organize the vertices in a way that any edge goes from left to right in the order. Okay, so let's look at an example. Okay, now I claim that, so there are 6 vertices here. You can order them in a way that any edge goes from left vertex to right vertex. So in particular, okay, how will you prove this? There exists such an ordering. So the claim is if the graph is directed acyclic, implies there exists such an ordering. 。  . 。  . 。 . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . 。 . . . . 。 . . 。 . . 。 . 。 . let's try and prove this, right? If you have a directed acyclic graph, I want to claim that you can order the vertices this way, okay? So one direction is easy. Which direction is easy? Right to left. If there is such an ordering where all edges are going from left to right, there's no way you're going to have a cycle, right? Because yeah, they're all going in one direction. I claim that if it is directed acyclic, you can order them. And okay, the following subclaim is easy to show, that if you have a directed acyclic graph, I want to argue that there exists a source vertex, a vertex which has no incoming edge, and a sink vertex as well. So DAG G is a DAG, directed acyclic graph. Okay, so that's implies there exists a source vertex and a sink vertex. What is the sink vertex? No edge going out. And this means that no edge coming in. Okay, so suppose I prove this, then can you give me an ordering of the vertices so that all edges are going from left to right? What would be an ordering?
So we first find the source vertex, which is the source vertex.
Right.
Delete all edges. Then
Take the source vertex, give it number 1, pi of that vertex. Find the source vertex, make it first vertex in your ordering.
you have to also prove that deleting a vertex.
Yes, sure. That you delete, you have a DAG and I delete a vertex, it remains a DAG. Is that how to? You can't have, it's a subgraph, right? The original graph has no directed cycle, subgraph cannot have a direct cycle. So inductively you can order them from left to right. So make this the first vertex and you can order, right? Yeah, so if I show there is a source vertex or even a sink vertex, the same idea will work, that if you take the source vertex, give it number 1, delete it, look at the remaining graph, that is a directed acyclic graph, order the vertices according to the requirement, and then put this as 1. You know that all the edges are going from here to here because this is a source vertex. There is nothing coming in anyway. Okay, so why should there be a source vertex and a sink vertex? I'm sure you can come up with multiple different proofs. So look at the longest directed path. Okay, the starting vertex must be a source vertex, right? Or it must be a, is it not? Yeah. Right? Yeah, so look at the, okay, so let's say it is some longest directed path. And I claim that there cannot be any edge coming into S. Why? Where will it come from? If it comes from some other vertex, contradicts the fact that this is the longest path. If it is coming from somewhere else here, what you get is a cycle, since we assume there is no cycle. Same reason, that guy must be a sink vertex because you can't extend it. Okay, so if you have a directed acyclic graph, then you can do a topological sort. And in fact, the algorithm I described, find the source. How much time does it take to find the source? That itself could be like m plus n or something, right? There might be an adversary which gives you all edges going out of a vertex until the last one which is coming in. then you have to try this. Okay, so at least some n square algorithm you can come up with by using this, or or mn algorithm. Find a source, delete it, find a source, delete it, and so on. Right? But it turns out DFS gives you in one shot a topological sort. Okay, I should also give you this standard. It's a very important problem. So imagine that these are sort of prerequisite edges, right? So look, assume that A, B, C, D, E, F are some courses in some curriculum, and it tells you that to do D, you need to finish A. A is a prerequisite for D. So it could be algorithms, and you may have discrete math and theory of computing as prerequisites for algorithms. Algorithms may be a prerequisite for advanced algorithms, and so on, right? And but there may be some things where you don't need prerequisite. So there is, think of this as a prerequisite graph, and I need to decide some ordering to say, okay, which course I should take first. Then it gives you choices on these are the courses. You can do this, 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 and then go and do this course, and so on. So this topological sort gives you that. Okay. Another application you will see in your book is that, in the morning I wake up and I have to do various things. This is like wearing a belt or something, but before that I should wear a pant. Before that I should wear something else. Then I need to wear my shoes. I could do this directly. So there are all these prerequisites, and a topological sort tells you what is the order in which you should do these things. Okay. Okay. So as I said, this proof, finding a source and repeatedly deleting it, will convert into some simple MN kind of an algorithm. But what I want to tell you is that DFS actually gives you a one-shot algorithm using this property. So what am I going to do? So algorithm. Do DFS, output vertices in descending order of finish time. In fact, yeah, you don't need to even finish this and come. As and when you finish somebody, you just output it. Okay, and add it to the end of the list. Why is that? Let's see how I would do a DFS on this. Let's say I start at 1. No, let's be nasty and start at D. Why not, right? So I'm just DFS starting somewhere. So I'm going to say I'm starting at D. So I'm discovering at 1. This will take me to 2. Then I'll get here 3. Finish at 4. So I'm going to output E at this point because I finished first. And then I come to D, and I know that there is no more out of it, so that's finished at 5, and this is finished at 6. So when I finish, I will keep outputting things in that order. And so basically this is done. Now I pick some other vertex, let's say B maybe. I discover at time 7, go to C, which is at 8, no more. So finish 9, finish 10, and then I go discover this at 11 and 12. Okay, and then this algorithm says I'm going to output in decreasing order of finishing time. So it will be A, B, C, D, F, E. And as you can see, that all edges are going from left to right. And so why is this correct? Well, because if you, I mean, what do I have to prove? That if there is an edge UV in the graph, then finish time, so the claim is UV is an edge implies the finish time of U strictly less than finish time of V, because greater than, right? Because I'm doing in decreasing order. Then only it will go from left to right. Why is that true? Because if UV is an edge, either it will be a tree edge, in which case FU is greater than FV, or at the time when you explored U, V was a black edge, so it was a forward edge. So again, that means that would have finished first before you got there. That was black, so it was finished. So FU will be greater than FV. Okay, so that's a very nice simple algorithm to do a topological sort. And you can use DFS to do what is called strongly connected components in a directed graph. So a strongly connected, so an SCC is a maximal subset of vertices such that in S there exists a directed path between any pair of vertices in both directions. Okay, so this is a stronger version of connectivity in undirected graph, because there you are only talking about connectivity in undirected sense. So let's look at this example. So I'm going to allow loops and stuff. So. Okay, so look at this directed graph. So I want to break this into a maximal set of vertices where there is a path between any pair of vertices in the induced subgraph, right? So those are the strongly connected components of the graph. So my goal is to, given a directed graph, I want to break it up into strongly connected components. Okay. So what are the strongly connected components here? FG, yeah, FG is a strongly connected component. Can I add any more? Because it's saying maximal, right? FG clearly is strongly connected. There is a path between. But can I add E? Because if I add E, I can go from E to F, but there is no path from F to E, so I can't add. And similarly, you can check that I cannot add any more vertices. I can't add H. H by itself is a strongly connected component. CD is a strongly connected component, and ABC is a strongly connected component. Okay. One property of strongly connected component is that if I suppose contract all the vertices of one component into a single vertex. Okay, so let's say it's ABE, and then I have CD, FG, and H. And if you want to look at edges between these components, there can be edges, there may not be any edge, but you can't have edges in both directions. So if for example in ABE and FG, there are two edges, but they are all going in one direction. And I claim that this must be the case, that if you take any two components, all edges must, if at all there are edges, they must be going in one direction only. Okay, so ABC and CD, there is one direction edge. Between CD and H, there is nothing, but CD and FG, there are two edges, one edge, but it's going in this direction. And FG and H is like this. Why? How would you argue that it cannot have edges in both directions?
There is then from suppose B there is, then I can go to that part cover, and suppose from from G there is, then I traverse to a path and then come back, so it becomes strongly connected.
Right. So it contradicts the fact that
They are different points.
what you have is a maximal set. So if I have edges in both directions, let's say between CD and ABE. Suppose CD and AB, if I have both directions, then this together is a strongly connected component, because you already told me that this is strongly connected. There is a path between any pair of them. There is a path between any pair of them. Now, to go from a vertex here to here, I can take this direction H and use the path inside. And to go from somebody here to here, I will go to that vertex which has an edge here, come back here, and then reach there. So I can reach any pair of them in both directions. So I could have merged them. So if I have maximal set of vertices which are strongly connected, then the edges have to be only in one direction.
You also claim that there can be no directed cycle.
That's the next thing I was coming to. Yes, I claim that you can if you contract, and so now I can design a new graph where I contract all of this into a single vertex and draw this edge, because I have already argued that all edges are going in one direction. Then we add that edge if there is an edge. Now that graph I claim is a DAG, directed acyclic graph, for the same reason, because if you have a cycle like this, then I could combine all of them into one single connected component, and there will be paths between any pair of them. Okay, so now there is a very clever algorithm, simply using this fact that these connected components, this contracted graph is a DAG, and so I can do some sort of a topological sort there. So the following algorithm we can try and prove that as well. I think the following algorithm gives you a So this was there have been several, at least a different algorithm before, but this was discovered later. What we'll do is do a DFSG, step 1. Then what we will do again, do a DFS of G reverse. G reverse is basically reverse every edge. And we're going to do G reverse, but the step 1 of the DFS where I said, look at the vertices in this order. If it's white, do a DFS visit, right? In that order, just look at them in the decreasing order of the finish time. And then the claim is that what you have, basically vertices reachable from every root.
The connected components will remain connected.
Yeah. So look at the DFS, how does this DFS, you start at a vertex and grow as long as you can. And if you cannot, you will go and pick the next vertex and you will grow, right? Each one would be a strongly connected component. Okay, so that's a claim. So let's see how you would do this on this graph. So let me just grow DFS here, starting somewhere. Let's say I grow at 1. At F I start. So it's starting at 1. Then I go to G, to H, time 3. And I can't go anywhere else, so I will sort of finish. Come back to G, I can't go anywhere else, so I'll finish here. Come back to F and finish here. Then I pick some other vertex. So in the first, when I am doing DFSG, no order, I just do it arbitrarily. So let's say I pick at A, B will get to 8, and then F would have been black at that time, so I won't even visit it, but E I can visit. So that'll be 9, and I'm done here, so that'll be 10, 11, 12. Thank you. Yes. Okay, so A7, 8, then I go to 9, finish this 10, and then I come back here and I can go to C. Yes. So I will discover C at 11, D at 12. These are all done anyway, so I'll finish 14 and finish. Sorry? Oh, A is finished afterwards, so 16, not 12. Okay. Yes. Okay, so I start at F, go to G, go to H, finish, finish, finish. Then I start at A, then I go to B, go to E, finish it, come back and say I can visit C, D, come back to C, and then come back to B and come back to E. Okay, so this is how I do it. So I've done my DFS starting, arbitrarily started at F, and this is my thing. Now I'm going to grow DFS of reverse of this graph. Let me draw the reverse just to make sure I don't make any mistake. So the reverse of this graph will look like B, A, E to B, and I have an F and G and an F to B, and I have C, D, and C to B. Okay, and F to E. And there is G to C and H to G. Okay, so this is reverse of this graph. Now I am going to do DFS, but in the decreasing order of the finish time. So I am going to start at A. So this I will visit 1, then I go to E, go to B, no more, so I will finish. Okay, so I am finished with this. So what is the next thing I should start with? The decreasing order of the finish time. So I should start with C, right? Because 16, 15, 10 is all done. I should start with C. So I will have 7, 8, 9, 10. Then I start with in the decreasing order, so I should start with F. So it will be 11, 12, 13, 14, and this will be 15. Okay, so what are the components I visited? Well, I sort of finished here. One component, and this was a component, and then this was a component, and this was a component, and the claim is that these are the strongly connected components. Okay, so it's a very clever algorithm, and it's not very hard to prove as well. We will use again the fact that you have this sort of a DAG when you contract these vertices, and decreasing order of the finish time gives you the topological sort. Okay, so what do I have to prove now? I claim that U and V are in the same strongly connected component if and only if they are in the same DFS tree. After step 2. Right, after doing this is what I have to prove, right? So one direction is again easy. U and V are in the same connected component. Yeah, so suppose U and V are in some strongly connected component. Now, in your DFS tree here, there must be a root which should be able to, exploring these two vertices. Take the so if U and V are in the same strongly connected component, I want to claim that they are in the same tree at the end. Is that clear? Yeah. So in this DFS tree, it visits all vertices. This is a forest, not a tree. This forest starts somewhere, visits, and so it visits all the vertices, right? So there must be one tree which starts somewhere and visits U, let's say. So there is some in the second step. There must be something which starts at R and visits U. So what does that mean? That there is a path from U to R, right? Because this is in the reversal thing in the directed graph. Yes, okay, good. No, you don't know. You don't even need this. So there is a tree which starts from R and ends at U. Now, since U and V are in the same strongly connected component, there is a path from V to U, right? There is a path from V to U. There is a path from U to V. Since U and V are in the same strongly connected component, in the directed graph, there is a path from V to U. So in the reverse graph, there must be a path from U to V. So V should also be reachable from R. So U and V will be in that same tree. Okay. So this is what I want. So if U and V are in the same component, then look at that tree which visits U, because every node is visited in this DFS forest. And if U is visited, since there is a path from V to U in the graph, in the reverse there is a path from U to V. So R should also visit V, and so U and V must be in the same connected component in this guy. Now, converse is where we will use some DFS properties. Right. Conversely, suppose U and V are in the same. There is some tree where U and V are in the same DFS tree here, and I want to show that they are in the same strongly connected component. What does that mean? What do I have to show? And there is a path from V to U. Okay. Now this is happening in the reverse, right? So there is a path from U to V is clear, because you can go from R and then come back to V. This may not be a simple path, but you can extract out a simple path, right? So there is a path from U to V in G. Now I want to argue that there is a path from V to U in G as well, then I'll be done. Okay, so here we will use the fact that you are looking at it in descending order of finish time. I see. So we will actually show that there are paths from G, from R to V, and R to U and R to V in. How does that help? Yeah, so this is because they are in the same DFS tree, so you can in original graph you will have a path from U to V. Now to show that there is a path from V to U, what I want to say is that there will be a path from U to R and V to R, and so you go from U to R and then sorry, okay, how does that give you right? No, okay. There exists a path from U to R and V to R in G. Okay, let's capture that. Good. I think I'm jumping ahead. Now what we want to show that there are paths from R to U and R to V as well. Then we will be done. The claim is there exist paths in G from R to U and R to V. Now combine these two, you will get a path from U to V and V to U. So because you can go U to R and then R to V to get a UV path, V to R and R to U to get a VU path. Okay, so I want to claim this. Okay, now look, you started in decreasing order of finish time in your original DFS, remember? So that means the finish time of R is greater than finish time of U and finish time of R is greater than finish time of V in original DFS. Right? Because you were exploring this in the reverse in decreasing order of finish times. So if this finish time was larger, you would have started here and not here. Okay? And does that tell you anything? That finish time of R is greater than finish time of, we have removed the properties here. What does that mean? In your, so there are two ways it can happen. So I was in, when I was growing R, I got U so that U finished first. So U was a descendant of R in one of the original DFS trees. So U finished first and then finished R, which means that there is an R to U path. Okay, this is one possibility. If this is there, I am done. The same argument will work for V. What is the other possibility? That R finished before U. Sorry, U finished before R. That means that U was some black vertex, it's finished, and R finished much later. That means that there is really no R to U path, there is no U to R path in G. There is no U to R path in G because, like I said, if this happens, means that U finished before R means that U is a descendant of R, which is good news for us because that gives me an R to U path, one of the claims I had. Or U finished before and then R was exploring it, that means that R could not be reached from U at all because I would have just put it here. That means there is no U to R path, which means that there cannot be an R to U path as well. There is no U to R path. Yes, exactly. But we assume that there is a, we proved that there is a U to R path. That's a contradiction. Right? Which implies that there is no UR path, a contradiction, or U is a descendant of R in original DFS, which implies that there is an RU path. Similarly for V as well. So that's a that's a slick proof, but really what's happening is that we are using the fact that when you contract this, you have a topological sort, and so if you do it in reverse decreasing order of the finish time, basically that the edges, the edges are all going from here to here, but those guys hence cannot be reachable from here. If you can't get to that vertex, that means you got your strongly connected component. Okay, so that's the argument. Okay, so these are some nice, powerful applications of DFS, using which you can find strongly connected components. So there is an undirected version of strongly connected components called biconnected components, which are a maximal set of edges where there is no cut vertex. Okay, you can take your cut vertex algorithm and modify it to produce them as well. Okay, so these are all some more or less. So this is like a 2 DFS.